Hello everyone, welcome back to Decking Cards. So right now we'll be taking a look at the final problem of day 1 of the IMO 2025. This is a really interesting yet manageable number theory problem. Without further ado, let us take a look at the problem statement. So problem 3 is as follows. Let n denote the set of positive integers. A function f from n to n is said to be BONZA if fa divides b to the a minus fb to the fa. Very interesting. For all positive integers a and b. Determine the smallest real constant c such that fn less than or equal to cn for all BONZA functions f and all positive integers n. Okay, so you want to look at all possible BONZA functions and see what is the tightest linear bound you can put here. Okay, typically in my videos, I will actually have a motivation section. But in this case, this problem is actually quite straightforward in the sense that as you motivate yourself to investigate, you actually end up with the solution. So I won't be having a separate motivation section, and instead I will be going through the solution directly and weaving in the motivation along the way. So as with functional equation questions like this, you will want to try special cases first. So one natural special case you will do is to plug in b and a to be the same thing. So if you do that, you get fa divides a to the a minus something about the power of fa, but of course that is divisible by fa already, so you get fa divides a to the a for all a. Okay, we can be even more special in this case because we are working over the integers. And what are special positive integers? Prime numbers. So if you use prime numbers instead, then in particular fp divides p to the p for all primes p. And this is useful because you know how to look at factors of p to the p. They are all powers of p up to p itself. So fp is equals to some power of p where the power is between 0 to p. I'm going to let cp denote the power. Very good, we have some structure to this function equation now. We can actually consider a few cases. The most trivial case is if all the powers are equal to 0. So case 1, let's say all the powers are 0, meaning to say fp equals to 1 for all primes. Let's start with this easy case and see if we can learn anything. Well, if we plug in b equals to p, that's a very natural thing to do because now we have fp equals 1. We can put 1 here and it will greatly simplify this term. You will see this as a recurring trick throughout this problem. So it motivates you to plug in b equals to p. And so for every a, you have fa divides p to the a minus 1. Now this looks very suspicious because this, if you fix a, this is supposed to hold for every p. 2 to the a minus 1, 3 to a minus 1, 5 to a minus 1. Surely the GCD of all those terms is going to be 1, right? So indeed, we can show that if fa is bigger than 1, then this means that some prime q must divide fa. But then fa must divide that q to the a minus 1, which is a contradiction because you cannot have q divide q to the a minus 1. Okay, so therefore fa equals to 1. This means that fn equals to 1 for all n. Okay, this is not a bad start. For case 1, we already force ourselves to say that the function f must be fn equals to 1 for all n. Very good. Let's look at another case. On the other extreme, maybe we can have this power being more than 0 for infinitely many primes p. There's still one more case coming up, which is that if the power is more than 0 for finitely many primes p. Okay, so far we look at more than 0 for no p. Now we say infinitely many p's. The third case will be finite and positive many p's. Okay, so let's look at this case first. If this power is bigger than 0 for infinitely many p's. Now, this time, I'm going to plug in A equals to P. And it's quite obvious that you want to do this because if you plug in A equals to P here, at least you know that you will have P appearing on the left side. Okay, because now FA is some power of P, which means P itself will divide whatever is coming here. So, and the thing that comes on the right side is B to the P minus FB to the FA. FA is P to your C over P to the CP. Okay, yeah, it's quite a tongue twister. So what do we learn here? The nice thing is that you have P's at the top. So if you remember your Fermat's little theorem, anything to the power of P is congruent to that thing itself when you look at mod P. Okay, so you might be familiar with the A to the P minus 1 congruent 1 format, but if you multiply both sides again by A, right, then you get A to the P congruent A, right? So in essence, anything to the power of P is congruent to itself. So B to the P will be congruent to B, and this thing, you just need to apply Fermat's little theorem multiple times. So because this is basically FB to the P to the P to the P to the P, yeah, so you get the point. So if you do it multiple times, you'll get FB. So P divides B minus FB. Now, this tells us one thing. If we fix B, we must deduce that B equals to FB. Why? Well, because if B is not equals to FB, remember that this holds for every single of this prime for which CP is more than 0. Yeah, I should mention here that when I plug in A equals P, I'm talking about such P's where CP is bigger than 0. And since there are infinitely many of such primes, I can pick a P that is arbitrarily large. So if this is not 0, you will get a contradiction because this is supposed to hold for some arbitrarily large P. Therefore, we conclude that Fn must equal to n for all n. Okay, this is really not bad. I just consider another case and I very quickly deduce what the function f must be. So I'm just left with the third case. So if you are in the IMO and you're doing problem 3, at this stage you'll be like, wow, I think I've gotten at least 2 points out of 7. So looks like this is going well. So let's look at the last case, which is CP is greater than 0 for positive but finitely many primes P. I should write a positive number here. Okay, so I'm going to let capital P be the set of such primes where CP is greater than 0 and capital Q be the set of the other primes. So capital P is non-empty but finite in size. Capital Q is infinite in size. Okay. Naturally, the thing you want to do is plug in. Now we combine the techniques from the first two cases. We plug in A equals to P, where it's in capital P, B equals to Q, where Q is in capital Q. And this is because then what we have is FQ is equals to 1. Right, because now CP is 0 CQ is 0. While on the left side, FP is some power of P, so P itself obviously will divide the right side. So P divides Q to the P minus 1. A very nice equation. And same thing, you apply Fermat's little theorem. Q to the P is congruent to Q itself. So P divides Q minus 1. This should look very suspicious to you because this is supposed to hold for all P in capital P and all Q in capital Q? Well, let's see what we can learn. This tells us that if we fix any Q in capital Q, remember this holds for every P in capital P. So in particular, the product of all such P's must divide Q minus 1. If you think about it, this looks very suspicious. Like for example, if capital P has the primes 2 and 3, you're saying that 6 is going to divide all other primes minus 1? Nah, that doesn't look like it's going to happen. And it looks like this is going to be problematic in most scenarios. And indeed, if we define pi to be the product, and if this product is bigger than 2, then by Dirichlet's theorem on arithmetic progression, there are infinitely many primes of the form prime congruent to minus 1 mod pi. And of course, because capital P is a finite set, this means that among all these infinitely many primes here, they must include some prime in capital Q, which then gives a contradiction because that particular prime Q in capital Q is congruent to minus 1 mod pi. Then obviously if you take Q minus 1, it's congruent to minus 2 mod pi, which will not be 0 mod pi, right? Unless pi is 2. That's why I have the larger than 2 here. So the only scenario left is that pi equals 2, which means that capital P is just the set containing the prime 2. Remember, in this scenario, P is non-empty. Wow, that is a huge restriction or reduction. So now we are just left with this scenario. F of 2 is a power of 2 where the power is 1 or 2. As for all the other primes, Fp equals to 1. Great. How about non-primes? Well, let's apply the same trick again. We want to learn something about non-primes. Let's put the non-primes here, but put a prime here so that my Fb is equals to 1. So I plug in B equals to P that is not 2, and I get a very simple equation. Fa divides P to the A minus 1. Okay. We do the same trick. Remember, P is supposed to be flexible here. So this equation is supposed to hold for P equals 3, P equals 5, P equals 7, P equals 11. And again, the GCD is probably something very restricted. So exactly the same trick as before. If Fa this time is divisible by some prime that is bigger than 2, we have a problem because then Q is supposed to divide this for every prime, including Q itself, but that is not going to happen. Now notice that this time, because P is going to be greater than 2, so I can only make this conclusion for factors that are bigger than 2. Or rather, specifically prime factors that are bigger than 2. So I'm not able to conclude that Fa equals to 1 this time, but Fn is therefore only divisible by 2 as its only prime factor. So Fn must be a power of 2 for all n. Okay, we are making progress. This is another huge discovery and huge restriction. Now that we make this discovery, let us flip the roles around. We now plug in A equals to 2 and B odd. And why would we want to do this? Actually, it's a very straightforward idea because if you apply A equals to 2, at least you know this side, what is the factor that you're looking at, is 2 or 4, right? So 2 or 4 divides the right side. And why do we put B odd? Because we can learn something. See, if B is odd, then this thing is odd. But the divisor here is 2 or 4. So FB must be the same parity as B. This tells us that FB must be odd. And together with the thing above here, we learn that Fn is equal to 1 for all n. Odd n. You see? Because it must be odd, but it must be a power of 2. The only possibility is 1. Okay, very good. We have settled half of the domain. All the odd numbers we know. Okay, so what can we do about the even numbers? Let's put our discoveries here. So we have learned that for the even numbers, it is going to be a power of 2. Odd numbers, the result is 1. Of course, what do? We want to learn about even numbers. Let's plug in the even numbers as A. And we plug in odd numbers as B because FB will simplify to 1. So we get, again, a very simple equation. Left side is your power of 2. Right side is B to the A minus 1. You might think, okay, we have to look at all the possible odd B to learn something. But turns out that just looking at B equals 3 is enough for you to control the size of CA. Let's think about this. If we want to control the size of CA over here, we have to figure out what is the largest power of 2 that is going to divide expressions like this. So the natural thing to do is to look at A as a power of 2 first. This will come when you try and do some case work by looking at different values of A. So I'm just going to skip to the result that we want to prove. So what we want to prove is 2 to the k plus 2 divides 3 to the 2k minus 1. So this term here, remember now I just specialize first where A is a power of 2. When the A is power of 2, 2 to the k, the largest power of 2 that will divide this term is 2 to the k plus 2. Okay, so basically this is what this is saying. If I increase the power 1 more, it will not divide. And the proof of this is very easy. You might say, why am I wasting time? I can just use lifting the exponent lemma, and that is like the new cool theorem that is being used in all the Olympiads. But if you are like me, I never figure out how to memorize all the different cases of the LT lemma. So you can actually prove this directly by induction. So what you do is the base case is very straightforward. Then if you already shown the case for k minus 1, you notice that for the case k, you can factorize this. This is just a squared minus b squared expression. By factoring like this, you have your induction hypothesis for this term. This term is only 2 larger than this. So if this is divisible by some power of 2 that is bigger than 2, then this is exactly divided by 2 and not any power larger. So this only contributes 1 more increase to your power. So it's actually very easy to show this by induction. And now for general case where A is of the form 2 to the k times m, where m is odd, you again want to find out what is the largest power of 2 that divides it. And it's actually the same. 2 to the k plus 2 is the answer. So how do we show this? It's very straightforward again. You can use lifting the exponent lemma right from the beginning, but I like syntactic approaches. So this is actually very easy to prove as well. You factorize this as the a to the m minus b to the m type of expression. So by factorizing it as follows, you have this part here, which you have proven in the earlier statement, and this part here, which is an odd number of terms, sum of odd number of odd terms. So this is actually just odd, so it doesn't contribute any factor of 2. Okay, so having proven all these things, what is the point? The point is, if we write A as 2 to the k times m, where m is odd, then the largest power here that can go in here is k plus 2. And this let us bound FA, because FA by definition is 2 to the CA. CA at most is k plus 2. If I take out the common factor of 4, I have 4 times 2k, which is less than or equals to 4 times 2k times m. N2K times M is your A over here. So I've shown FA less than equal to 4A. So far, everything is quite intuitive. And so if you combine the three cases that we have checked, first one being Fn is going to be equal 1, Fn equals to n, then Fn less than or equal to 4n. So the smallest so far we have seen is C equals to 4. Now, of course, to complete the proof, you are not going to throw away 1 mark like this. You need to find a construction to show that that is the tightest possible bound. And it's actually very easy to motivate the construction by working backwards from here. Now, I will skip how you might motivate yourself, but in essence, if you work backwards, you might see that using this as tight as possible, you'll get 1, 8, 1, 16, 1, 32, and so on. You will notice that actually if you put 8 here, it doesn't work. If you change to 4, it will actually work. But to make our lives very simpler, we only need some construction that hits the bound. And the easiest construction to prove would be to make all the even numbers 2 and just use 16 for F4. So I set F4 equals to 16, all other even numbers as 2, and all the odd numbers as 1. So if you didn't get the motivation, you can think about it later. But right now, let us check that this construction works. It's very easy to check because if A is odd, then F1 is just 1. Obviously, this is going to work. If A is even, where the even number is not 4 itself, then the left side is 2. And in our construction, B and FB have the same parity. You can just take a look here. So it also works. The last bit that is slightly tricky is if A equals to 4, so we need 16 to divide this for every B. Now, if B is even, then we just have even to the 4 minus even to the 16. So obviously, 16 divides this. If B is odd, then we have 16 divide B to 4 minus 1. We need to show this, and this is true because you can factorize this as follows. Between this and this, one of them is divisible by 4, the other is divisible by 2, and this is divisible by 2. So that is the end of the proof. Now, this is problem 3, supposed to be the hardest problem of day 1. But actually, this problem seems quite motivatable. The solution can be motivated. As you start exploring, you will start inching closer and closer to the solution. So it doesn't feel like it's as hard as a typical problem 3. Well, I could just be lucky in getting to the solution. So let me know what you think in the comment section below. Stay tuned to the channel for the day 2 problems, and I will see you soon.